Hello everyone, and welcome to the fifth lesson in our series, Waves in the Real World. In the previous lesson, you were introduced to the Doppler effect, which explains the change in sound that we hear when some sound sources move past us. In this lesson, you will learn how the Doppler effect is actually put to use in our everyday lives. By the end of this lesson, you should be able to apply the Doppler effect to various real-life situations, apply your knowledge of waves to solve real-life problems, and discuss the pros and cons of using the Doppler effect in traffic law enforcement. You should recall that the Doppler effect describes the change in frequency that is observed when a wave, a source, or an observer are moving relative to each other. We learned in the previous lesson that the observed frequency can be calculated using the following equation. FO equals V plus VO over V plus VS times Fs, where VO represents the velocity of the observer and Vs the velocity of the source of the waves. The variable Fs represents the frequency of the waves as they leave the source, and FO the observed frequency. The speed of the waves is represented by the variable V. We also learnt that the positive direction in the frame of reference is defined as the direction from the observer to the source. The signs of all the other velocities must be worked out according to this frame of reference. In this lesson, we will look at some real-life situations where the Doppler effect is applied. The first application that we will look at is a medical application. The Doppler effect is used to measure the rate at which blood flows through a person's veins. This knowledge can help to prevent fatal heart attacks and strokes. We use ultrasound waves that have a frequency of about 5 megahertz. Ultrasound waves are sound waves that are too high for our ears to hear. A transmitter sends out these ultrasound waves, which are aimed at the blood in the veins. The waves pass through the walls of the veins, but are reflected by the blood cells. The ultrasound waves striking the blood cells have the same frequency as the transmitter. However, the blood cells are moving, so they act as a moving source for the reflected ultrasound waves. The reflected waves are picked up by a receiver, and the difference between the transmitted sound and the reflected sound is analyzed to provide information about the velocity of the blood cells. Would you like to have a go at applying your scientific knowledge to medicine? How do you think the frequency of the received wave will differ from the frequency of the wave that is reflected from the blood cell if the blood is flowing away from the receiver? Well, we first need to work out our frame of reference. This diagram shows us the observer, in this case the receiver, and the source, the moving blood cells. We will just focus on the horizontal components. Remember, the positive direction is taken to be the line from the observer to the source. So in our diagram, the positive direction is towards the right. Now, let's write down our given information. Since the receiver is not moving, we know that the observer velocity is 0 meters per second. The blood cell is the source of the wave, and it is moving away from the observer, so its direction is positive. If we substitute the value of VO equal to 0 into our Doppler equation, then the denominator of the fraction is larger than the numerator. So we will be multiplying the source frequency by a number that is less than 1. Remember, the frequency of the source, the moving blood cell, is the same as the transmitter, which we know. This tells us that the observed frequency will be lower than the frequency of the sound waves at the source. The receiver used to pick up the reflected ultrasound can be tuned in to the lower frequency very accurately and can measure it. So using this ultrasound apparatus, we know both frequencies, FO and FS. The speed of the ultrasound in blood is also known. This means that the only unknown value in the equation is Vs, the speed of the blood cell. By substituting in our known values, we can easily find the speed. The Doppler effect is used in a similar way to measure the heartbeat of unborn babies that are about 2 months old. The second real-life application of the Doppler effect that we will look at in this lesson is in the area of sport. Have you ever wondered how the television studio can tell us the speed of a cricket ball as it leaves a bowler's hand?
A drop in pace.
Or have you wondered how the speed of a tennis serve is measured? In both of these examples, a device called a radar gun is used. This device sends out a signal in the form of a radio wave. The radio signal is aimed at the moving ball and is reflected by the ball back to a receiver. The difference in the frequency of the sent beam and the received beam is analyzed using the Doppler effect equation to give information about the speed of the ball. An important thing to note about using a radar gun is that it needs to be lined up with the movement of the target that it is measuring. When the angle of the radar gun with the target's velocity direction is wide, the measurement of the target's velocity will be less accurate than when the angle is smaller. So radar guns need to be handled correctly to give an accurate velocity reading. Let's move on to look at another very interesting area where the Doppler effect is applied, the field of astronomy. For this, I've arranged an interview with an astronomer, Marion West, from HeartRadio. Hi Marion, thank you so much for meeting with us. Could you tell us more about how the Doppler effect is used in the field of astronomy?
Yes, you can split light into the different colors of the rainbow. It's called a spectrum. And then for the different kinds of molecules, in a star like the Sun, you've got molecules like hydrogen and helium, which are the most common elements in the universe. And then you've also got what we call heavier elements. In astronomy, we actually call these metals. But for each element, it will have a particular fingerprint. Now, you don't only have the visible light available to you, but you actually have towards the longer wavelength side, the infrared, which is heat, and the radio waves, and towards the shorter wavelength, higher frequency, you have the ultraviolet, X-rays, and gamma rays. And for each molecule or atom, they will have a particular fingerprint. Now, this comes out either as a bright line in the spectrum, or it can come out as a dark line if the light from that molecule is actually being absorbed by gases higher up. So we can actually tell exactly what kind of molecules are in a star like the Sun, and from the lab we know exactly where in the spectrum these molecules, the light from these molecules, is going to occur. So if a star is moving away from us, you'll actually find that that line that you've been looking at will be shifted towards the red, and which is the longer wavelength side. If the star is moving towards us, it'll be shifted towards the blue. So it is a Doppler effect like you've been talking about in your program, but actually in the light region of the spectrum.
In other words, if we were to compare the line emission spectrum produced by helium from a discharge tube on Earth, it would look different from the line emission spectrum produced by helium in a distant star. That is very interesting. In our series earlier, we discovered that when the wavelength of a wave is longer than we expected it to be, it meant that the source was moving away from the observer, according to the Doppler effect. Does this red shift mean that the stars are moving away from us?
Yes, certainly. An astronomer called Edwin Hubble actually discovered that not only are stars moving, well, the stars will be moving towards and away from us because we're all circling around in our galaxy, but now galaxies actually can be moving towards us or away from us. Now, some of them, we're in a local group of galaxies, so some will be moving towards us and some away. But the further away you look, the more you find that the groups of galaxies are actually consistently moving away from us, which means that the universe is actually expanding. And Edwin Hubble was the first person to actually put the facts together with the theory, and that is really one of the strongest bases of the Big Bang theory.
Could you tell us a little more about the Big Bang theory and how it is supported by evidence that suggests that the universe is expanding?
The whole of the universe was included or taken up in this very, very small, high pressure, very hot ball. Now, often people think of, well, this ball then expanded into space, but in fact this ball was space and time and everything that is. So this then expanded, it expanded very, very quickly initially. We needed to have expanded very quickly because everything, as far out as you look, things are what we call homogeneous and isotropic. That means that in every direction that you look, everything is much the same. You do get clusters of galaxies, but on the larger scale, everything is actually pretty much even. So the universe expanded very, very quickly, and then it actually, obviously, as it expanded, it cooled. And initially, things would have been so hot and the pressure so high that you wouldn't have even had the individual atoms wouldn't have been existing. There would have been quarks and the stuff that make up atoms kind of all in a huge, very hot, very high pressure soup. And then as the universe expanded and cooled, so eventually atoms would have been able to form, but at that stage things would have still been hot enough that matter would have been turning into radiation and radiation into matter. So you wouldn't actually have been able to see back into that time at all. Eventually, I think after about 1 billion years, then your atoms and your matter and your radiation would have separated, and at that stage we could perhaps see back to when the first stars started to form and that sort of thing. We can actually, with our current telescopes, see back to when the first galaxies formed, some of the very early galaxies, but we still don't have answers to the questions like when did stars form first, or did galaxies form first? So the square kilometre array, which they're going to build, is going to be the biggest radio telescope in the world, and it's only going to be built either in South Africa or in Australia. They're still busy weighing that up. Yeah. That is one of the things that is going to try and look back to the very, very early time just after the Big Bang and try and answer those questions. But one of the supporting evidence pieces that you are looking for is that wherever we point a radio telescope in the sky, you get a uniform radiation. It's a very cold radiation. If you think about our zero temperature being cold, this is now minus 270 degrees, this radiation. Yeah. So, but it is exactly what theory predicts would be there as the cool down radiation after the Big Bang, because the universe has been around. Initially, when Hubble did his calculations, the universe came out to be about 2 billion years old, and that was a problem because we knew that some of the rocks on the Earth were about 4.5 billion years old, so the Earth was older than the universe, which didn't make any sense. But as we've gone on and refined the measurements, we've actually now got a value for the age of the universe of 13.6 billion years, so obviously the solar system at 4.5 fits in very well with that. So with all the supporting evidence, we can conclude quite clearly that the universe is about 13.6 billion years old, and that the Big Bang theory is the best theory that we have of the universe at this point in time.
Thank you so much for speaking with us today, Marion.
It's been a pleasure.
I'm sure that you found that interview just as fascinating as I did. Now, I think it is time to move on to your task for today. Earlier in this lesson, you learnt that radar guns are used in sport to tell us the speed of a moving ball. Radar guns are also used in traffic law enforcement to fine people who are traveling above the speed limit. Your task for today is to think about and discuss the pros and cons of the use of this technology in traffic law enforcement. To give you a bit of background for your thinking, have a look at the following interview.
I'm Ronald Wright from Syntel, and basically Syntel does we're a supplier of road safety and traffic management and revenue collection services for the local governments in South Africa.
Could you tell us, what are the historic practices in speed trapping?
Years ago, we used to do speed trapping by means of stopwatches and not linked to any photographic evidence. That's the prime difference between previous technologies and the technology of today. Today we use mainly two methods, laser technology and radar technology. Popular belief within the community is that we're using mainly radar, because in newspaper reports you always talk about radar technology. In fact, it's laser technology which is predominantly used in this country. Probably about 95% of all speed measurement is done with laser technology in this country today.
And what are the accuracy and validity of current methods?
The measurement must be accurate to be able to be used for enforcement purposes. You must be within 2 kilometers below 100 kilometers an hour, and above 100 kilometers an hour you must be less than 2% within that accuracy range. So if you're traveling at 200 kilometers an hour, you must be within 4 kilometers of the true speed of the vehicle. The reflection of the laser beam needs to have a very flat surface on which to reflect, and normally they would aim that laser beam at your number plates. You can aim it on any flat area of within the area of the number plate. Legally, that's what we have to comply with. So the guy aiming the laser gun has to be very accurate on a moving vehicle traveling up to 220 kilometers an hour. So it takes quite a bit of practice to do that. Radar technology is a system where they would beam an electromagnetic radar beam towards your vehicle. In the past, they used to use long-distance, high-powered radar. In the later technology, they would use a slant radar, which is a beam aimed slightly at an angle of 20 degrees across the road. And this would be a low-powered radar in the later technology. In the past, the high-powered technology was more prone to reflections of other vehicles within its path, and quite often these cases never stood up in court, so they decided to go for a radar, slant radar, which is a low-powered radar beam. This is more effective because in the past people used to use radar detectors, and you could detect a radar speed measuring device a few kilometers ahead of the speed trap. So with this new technology, you can't detect the radar until you're right within the beam.
What is the impact of modern equipment such as radar detectors and jammers, which drivers might have to avert law enforcement?
Okay, technology today provides, a lot of people are actually using laser jammers. You normally find this in sports cars and the upper range or the price brackets of motor vehicles where people can afford to put these jammers in. They roughly cost about 5,000 Rand to install a laser jammer into your motor vehicle. What we have developed is a system where we use a combination of laser and radar technology to catch offenders speeding and to prosecute them for using jammers. So we then take those two evidence, the guy being speeding on the radar camera, we will get his reading on the speed on the radar camera, and in the case of the laser camera, certain laser cameras are equipped to recognize when that pulse has been jammed or blocked, and we will then, in any case, whether the guy, regardless whether the guy is speeding or not, we will then take a photograph, and it will indicate on the photograph that the signal has been jammed and no accurate speed reading could be taken. So it's basically a self-test within the camera as well, so that you can't prosecute somebody for when the signal has been scrambled. Usually, in the case of certain cameras, we will get a reading of 65,000 kilometers an hour, which we know is a false reading, but we will then prosecute based on having a jammer in their vehicle. But these will be done in special operations.
Trapping and fining people who speed means that they are punished after they have committed the offence. Does the Traffic Department have any strategies that try to prevent people from speeding in the first place?
Right, we as a service provider to the law enforcement, we are tasked there to do the dirty work and to actually catch the offenders speeding. There is, however, the responsibility of the Department of Transport to try and to do the preventive measures. This is why Department of Transport has appointed Arrive Alive to basically run with a media campaign to educate the public. I think the first point is education. We need to inform the public that speed and high speed actually creates higher injuries or more intense injuries on the person's passengers within the vehicles. So I think you've seen evidence of that on the highways, where you'll see motor vehicles crashed and you see people maimed, and you see photographs of that. So we basically try and warn the public, and I think it's been quite effective over the past, since the campaign started about 3 years ago. There's been a fall of 7.4% in the number of fatalities on the road. So the campaign has been effective. They started with the Arrive Alive website, which is very informative, and they have numerous studies which have been conducted and documented on that website in terms of statistics, road accidents, and various pedestrian fatalities, and all those areas of road safety have been highlighted on this media campaign.
Thank you for joining me today. In our next lesson, we will look at a few other ways that the Doppler effect is used to explain some real-life scenarios, such as the loud bang that is heard when a jet aircraft breaks the sound barrier, and the loud, sudden noises that thunder makes. Don't miss it.